So welcome everybody to the February edition of Kanban-TO, and well, I'm very happy to have today Chris Chapman as our guest speaker. So I've known Chris for a long time. Not sure, I was trying to remember how long, but I've known him from various agile circles here, but I've always known him to be a very engaging and very insightful speaker. So I'm really happy to have him here. For those of you who might not know him, he's based in Toronto, and he is a big proponent of systems thinking, and especially the teachings of Dr. Deming. So really happy to have him here and see how we can, talk about variation this time. So Chris, floor is yours.
All right. Okay, so just gonna get that out of the way. Understanding variation for Kanban practitioners. A little bit of a quick talk that I threw together. Fernando reached out to me about this last year on the tails of Mike's great talk about Jira metrics. And we had a little bit of a confab after that, and it was suggested that maybe I could do this and dovetail in a little bit to what Mike was doing. Because he presented something that was really interesting about how to surface interesting team and flow-based metrics from Jira without having to use the admin portal. You could do it through the API, and he was producing really great reports. So that's what this talk is going to be a little bit about is, okay, let's talk about flow metrics, but in an entirely different way about how it works with variation. So this is a little bio about me. I think I know everybody here, so I don't need to go over this again. It's okay. So I'll just move on to the next one. I'm just going to tell you about what we've got for our aim tonight. So we're going to learn a little bit about what variation is and how to visualize it with something called a Process Behaviour Chart. And that's because we want to be able to understand if our Kanban-managed processes are stable and predictable. And it was something that came up thematically with what Mike was talking about in his talk, about how his reports could help inform prediction-based guidance. So this is going to be a crash course. We're going to move fast because there's a lot of material to get through. But thankfully, this is being recorded, so you can go back later and you can go through the parts that you may not be getting on the first time through, maybe on the second or third try, because I'll be going through it kind of quickly. I'll also offer that right now is your opportunity to detour from this presentation, because this is sort of a red pill, blue pill moment. I can tell you that when I began learning about variation, probably about 15 or so years ago, and my progression in becoming better and better at it with deeper and deeper understanding, it's like the red pill moment. You will no longer be able to perceive data in exactly the same way, and you're always going to be wondering about what is it actually telling you. And this will pertain to data that you see in your organization, but also data that you're going to see in day-to-day life, that you may see in the media, anywhere where somebody is telling you, on average, this happened, or such and such surged by X% or dropped by X%. You're no longer going to be satisfied with that, and you're going to be driven absolutely crazy like I am. So here's your chance to bail. So the question is, are our processes being operated predictably? Inside of systems-based thinking, when we're applying it to Kanban method managed systems, we talk a lot about probabilistic forecasts that are based on past or prior data summaries. And they inform how we think about how that system might perform, or what we're going to communicate to our customers about how that system might perform in the future. It entails some dedicated efforts that we're going to be making in order to improve our practices. Maybe we're not delivering so hot. Maybe we want to deliver better. Our customers are asking for more. It's also, in all of this, it's an aspect of the quality of the services that we provide. So one of the things that I'm noticing is that when we talk about predictability, or whether our systems or processes are being operated predictably, the one thing that I've begun to perceive over time is that we are beginning to confuse the counting of things. Counting of WIP items, counting of cycle times, counting of lead times, counting of ages. And we're producing summaries based on that data, and we're confusing it as being analysis. And you're going to see what I mean later on when I say we're using the counts then to infer predictability. So we're aggregating some data that we are mining from how our processes are working, and we're presuming that that tells us with some degree of range of probabilistic certainty through various statistical methods that this is what we could expect in the future, our processes to work like. I have a contrary point of view. I said, not quite. What we're doing is correct. We shouldn't abandon the way that we are summarizing data. We need to actually complement it and understand, is the system that's producing those summaries stable and predictable? So this is where our education begins. Data generated by a process are random and miscellaneous. The knowledge that we build from analyzing the data is orderly and cumulative. And the purpose of our analysis is to get insight into how our processes are behaving. So let me step through that again. Data are random and miscellaneous. Knowledge, orderly and cumulative. The purpose of analysis is insight. These are, I've held on to these as sort of touchstones every time I do my analyses and try to understand why I'm doing what I'm doing. It's always because I'm trying to drive out some insight into how the process is working. So in this regard, we've got two types of studies that we undertake when we look at how do we analyze systems performance. We have enumerative studies and we have analytic studies. The enumerative ones concern counts of things. The analytics are about process behaviors. So enumerative studies answer the questions of how many, how much. They deal with counts, dispersions, standard deviations, percentiles, averages, histograms with confidence intervals, regressions to the mean, bar charts, etc. So what they are doing is the data that we are getting from our processes, Kanban method managed processes, describe a frame of data, but they don't describe why there are so many or so much. It's part of the missing puzzle piece. So here's an example, Little's Law. We have a relationship of averages. We all know this, the number of average number of items that we've got in the system, the average wait time, the average arrival rate. But what in itself, we tossed this summary statistic around a little bit. What does the average actually mean in each of these three elements? So averages, it shouldn't be too revelatory here. They express a midpoint in a data series. So in this chart here, we've got comparisons of three rather famous baseball players, Babe Ruth, Roger Maris, and Mickey Mantle. And you can see that what this is actually expressing is how many home runs per season did they hit for the time that they played. You can see Babe Ruth has got an average of 41.1, Roger Maris has got 22.9, Mickey Mantle has got 29.9. These all represent the effective midpoints, but there's a lot of data. You tell somebody that Babe Ruth on average got 41.1 home runs per game or over a season, per season over his career. Embedded in that is there's a range of figures both above and below the average. An average expresses that there is going to be a distribution where 50% are going to fall on one side and 50 on the other. But we use the average to communicate how well something may actually be working on the average. What's the average arrival rate? What's the average cycle time? But we're missing what the whole data series actually is, because averages, as with a lot of summary statistics, abstract away the time order. So we don't actually know the total span of time or the frequency within that span of time these results were being generated. These are all critical things to actually understand about predictability in a process. So here's another example. This one, I think we're all familiar with, the cycle time histogram. We've used it a lot. We aggregate cycle times for delivered items, and we plot them. Software makes this really easy. This one here tells us the canonical 85% confidence interval where we can expect items to be completed by, and in this case, it's 9 days or less. But what else is this actually telling us? We can see on this chart there's a long tail. In traditional enumerative study analysis, the items that we've got on the far right, we consider outliers, not necessarily representative about how the system actually works. If we really want to be able to communicate something to our customer, we can say, well, we have a high degree of confidence that no matter what comes into our system, it'll be done within 2 business weeks. Okay, so that's great, but is the system that produced that reliable? Is it predictable? If we go forward into the future, is it always going to be 9 days or less? There are items in this histogram which suggest the outliers. If we were to incorporate the outliers, they're important bits of information. But again, one of the things that this histogram abstracts away is when and in what sequence, what was the time order where these cycle times occurred, and why did they aggregate into this particular pattern? So the question is this process predictable? Here's another example, an aging whip diagram. Is this process predictable? So this shows us that we've got some work items that are aging very rapidly, and we see them in the 3 columns in red, and they're indicating we've got one at 7, looks like we've got one at 5, another one at 8 days in these various categories. Oops, sorry. Why is that occurring? Again, is the process that produces this particular pattern stable and predictable? Is it something that we would see going forward into the future? Is it something we could predict upon? In the work that I do, this sends up a lot of red flags, because we were basing predictions based on this. We would say, well, how do we know? By what method and what rational basis are we assessing that this gives us a picture about understanding how the process actually works? And this becomes even more of a problem when we try to think about, well, what happens when we make changes? Is the change an improvement or a regression? Here's another one, cycle time scatter plot, saying that 95% of things will be done within 20 days. That's a hell of a range. At least they've categorized it here where we can kind of see month by month across the bottom. April looks like things got a little out of hand, but it seems to be falling into a distribution, which is what we would kind of expect to happen. So at least we've got the benefit of knowing a little bit about the time series, but we still don't really know or have an accurate picture about, is the process predictable that created this pattern? Would we see similar patterns if we go from August to December, for example? Is there going to still be an aggregation? Is it still going to be 20 days, or will things have been pushed down to 15 or 10? Will a policy change have negatively or positively affected that? Would enhanced automated testing, would that change any of this distribution pattern at a specific point in time? It becomes difficult to make those kinds of assessments when you're using these kinds of aggregate summary visualizations. So here's another one. I kind of like these ones best out of all of the summary diagrams, because it doesn't remove the time order out of the data. You can see this one is comprised of 2 parts, where we've got the summary throughput histogram on the top with the 85% confidence interval. But at the bottom, we actually have the actual throughput data day by day expressed to us. And this is really kind of interesting to see, because now we get an indication of how does that system actually look with respect to items being pushed through. And I can look at that data. I've looked at enough data sets, and I can look at this and say, there are signals of instability. This is not a predictable system. So if I say, is the process predictable here? The question is, without the knowledge of understanding what variation is and how it affects processes, how would we ever be able to come to a conclusion? So I can see that there's a lot of variation in this. What's not entirely clear to me, I'm making a guess that the entire data series is summarized here. It's possible. It looks like it could be, but sometimes that's not what you want to do, because in this time series, the system could be performing very differently depending on where you land in that time series. So I'll show you what that actually means. I have an example of this, and I'm going to have to apologize because it is really grainy. I lost the original, but this is an example of that kind of histogram where I am moving a sliding window that recalculates the distribution for the throughput histogram based on a 30-day rolling sample. So where you move this, you can look at the variation occurring. Now, the thing to think about is probably the most reliable representation of how the system is working is that when I move it towards the final right, when you see the last 30 days. As it's moving across, think about making a prediction based on that 30-day window where the data is actually falling. Because the reason you wouldn't want to necessarily capture all of the data from the left to the right is because you're including things and you're missing out on a lot of variation that could have occurred and how the system is actually performing. So when we're sampling on a 30-day window, we're able to get a better understanding of, well, how is the variation in the process data itself affecting how the throughput is aggregated? So now you're seeing a relationship between the two. Now, it's kind of interesting is in this particular case, the 85% interval slides back. So it looks like the system almost goes back to an earlier state, and what was happening in the middle was actually a little bit more unstable. Something, again, like looking at this data, I can tell there are multiple signals, and this would be something that I want to have a look at. I have a hand.
Yeah, that's me. So we have a couple of questions here that perhaps are relevant for this point. So
Okay.
Rob is asking if do you always prefer daily throughput versus weekly or monthly? And connected to all that, I think it's a question or a comment perhaps from Nawaz asking about variation or I guess predictability in this context, if it's always good or bad. So in what context?
Okay, so I'll deal with that one first. Variation is everywhere, and I'm going to talk about that in a second. So there is out of control variation and in control variation. Being able to tell the difference between the two is important, but we can't escape it. Every system has variation. It's up to us to be able to understand it. For Rob, do I prefer, which do I prefer on for throughput, daily, weekly, monthly? It depends on the data series and what I want to look at. Actually, I will sometimes aggregate, and I have some of Mike's data. Mike sent me some data from his geometrics, sanitized geometrics data, and I actually looked at it at different timescales because I was wanting to understand the overall variation picture. You're going to see much more variation day to day, and that's easier to isolate. But sometimes you want to pull back out and you want to say, okay, well, how is this affecting how we deliver? You know, maybe we're delivering on a weekly cadence, or maybe bi-weekly, or maybe we are looking at releases that are going into production every month. So we might want to look on a more granular time scale, but always be open to shifting your analysis on different time scales because it's going to reveal different things. Sometimes day to day is going to be overwhelming. Probably minute by minute would just be crazy. So don't do that. Pull back out to where it makes the most sense. Okay, let me go back here. So the reason that I showed that last graph is because of a really important fundamental point. When we are dealing with process data, when we aggregate them into summary statistics or using summary statistics, we are presuming that it represents the alpha and the omega. It is totally representative of all the data that will ever be. In analyzing processes, we have to realize that this isn't the case because empirical evidence is like a stream. It is always going to be rushing day by day. New things are going to be occurring. The best that we can do is gather the data, keep it updated daily, and always be looking at it for signals of variation, which I'm going to show you how to do in just a few slides. But we got to get into understanding, well, how do we see that? How do we deal with the fact that empirical evidence is never complete? So that's where analytic studies come in. So this is the domain of prediction. We want to be able to understand if what is being produced in the summary statistics is stable. So we've seen these histograms, we've seen these scatter plots. They are suggesting to us with averages and standard deviations. This is the summary statistic that we are looking at. What this tells us is the process, when we undertake an analytic study, is the process that created it predictable and stable and could go on into the future. How would we know if a change was introduced in the middle of all of this, whether we had engendered or created an improvement in the process and an improvement in the summary statistic? We can't know that because we've stripped away the time series. Analytic studies are very focused on time series and understanding when in time order is really important. And finally, it answers a fundamentally important question about what is the variation in the process trying to communicate to us, because this goes latent. By exposing it with an analytical study technique, that's how we're able to understand it. So what is variation? We've been talking about it. I alluded to a little bit with the earlier question from Noaz about this. I think of variation as a universal phenomenon. It is everywhere, wherever we have things coming together to interact in some way or fashion that is going to result in a change. So this happens on a universe scale. This happens in nature all around us. For our intents and purposes, though, we're going to pull the scale or the scope way in. We're going to say, well, it's when it occurs between the interactions of people. So whether we're communicating through Zoom, or whether we're in a room together, or whether we're having to have multiple windows open, communicate with different people while running in another place, we're always trying to bring something together. We're bringing our knowledge together, our work product together, so that we can accomplish something. Whenever we have one or more components coming together in a unified way, in a systematic way, we're going to create the phenomena of variation and how those parts work together. So as this quote from Dr. Deming mentions from the New Economics, when do data indicate that a process is stable, that the distribution of the output is predictable? How will we know what is normal and what is abnormal in this pattern of variation? So some of you might recall my many times running of the red bead experiment, where we have a bucket and we've got 4,000 beads, 3,200 white, 800 red, and we're set up with a challenge to be able to sift out 50 white beads. But we come to understand, we set the system up so that this isn't really attainable. So we go through the charade of trying to say, okay, well, minimize the number of red beads that you pull while ignoring the inherent variation in the bucket. If people haven't played this game before, they come to realize it by day 2 that things are stacked against them and they're never going to get the $20. They're never going to get the top award. They're probably going to get stack ranked out of the company. Each individual who has ever played the red bead experiment is different from the other. They all have different skills, different experiences. Some played the game before, some haven't. Some are very fixated about trying to do the best possible job. Others enjoy it for what it is. They all interact differently, but no matter how they interact, they're all using the same equipment, and they're all coming out with a wide variety of results, anywhere from 4 to 19 beads per paddle, irrespective. So we're seeing that there's an important consequence that comes out of this, in that no matter how we try to adjust how individuals work together, the variation inherent in the system, that's owned by the system. So no matter what 6 individuals I give the paddle, they will all have a distribution that looks the same of red beads from game to game, because the majority of the performance belongs to the system. The minority belongs to special causes, like when people try to flick beads out or do obtuse things with the paddles. We begin to see that happen. So this is just a restating of this, what I call a leadership cheat code, which gives you a sort of a leg up on people in the industry, people in management. One thing they don't understand is this: they look for cause of problems first to the individuals who are working in the system, maybe a later consideration for the equipment that they're using, maybe a later consideration in how the team is composed, and maybe it's our culture and we've got to learn to live our values, etc. Things that don't really have anything to do with how well people can do their job. We're doing everything but changing the system. And that comes in the second part of this: no amount of skill nor care can overcome the system's design. Systems have inherent variation. We often say that if we're not happy with how our systems are working right now, rest assured it is designed to achieve those results as if it were a Swiss watch. If we want to change those conditions, we need to change the systems, the way the system governs the interaction of the people within it. So let's get to the nitty-gritty. We've got two types of variation, just like two types of studies. So in an analytic study, we're concerned with looking at routine common causes of variation in a process and extraordinary special causes. And they pretty much mean what you think. There is a way that a system is going to work every day, warts and all. We may not be happy with it, but it's the way that it works. It could be that every 4 days, something goes bang in the server room and causes us to lose time. Could be every 10 days, 15 days. Maybe it's 1 day here and 1 day there, but that's how the system is working. If we don't know how to see that, though, we'll miss that. Extraordinary special causes are things that can come from anywhere. So it could be a change in policies or procedures. It could be someone being sick. It could be a discovery of a latent bug in production. These are things that disrupt routine common causes. So here we've got a way to visualize this. This is a graph that idealizes the routine common cause variation as a series of 4 distributions. So you can see that each one vertically measures the frequency of the process output. We're seeing a perfect bell curve distribution. And then on the other side of the axis, it's the characteristic, it's the process output itself. Time is the Z dimension as we go through. So everything here, this is, I've yet to see a system, unless it was designed inside of a computer, that is able to have perfect variation like this. It doesn't really exist. But this is the basis point, or the foundation from which we can begin to extrapolate an understanding of, okay, routine variation should look kind of like this. In real life, the curves will be a little bit variant with each other. They won't be precisely all lined up neat and tidy. Now, by contrast, if we have an unpredictable, unstable system, the curves are going to be all over the place, with the tail of one interfering with the midpoint of another, or drifting off, completely off into space altogether. Or we could have, just as you see with the last one here, a very flattened kind of distribution with longer tails. This is where we begin to see systems that resist being able to be predicted against. But they operate. Every single day, there are systems that we work with which behave very similarly to this. And we often meet it with a bit of a shrug. It's kind of like, it is what it is. What are you going to do? In order to improve this, though, we actually have to be able to see how this variation is occurring over time. So here's an exercise for you to get an idea about how to feel the common cause versus special cause variation. So let me just see here. So if you grab a piece of paper, just at your desk, and write your name using your right hand. Let's see here. Try to write your signature out 10 times. And I want you to keep it as uniform down the middle of the page as possible, neatly on either side. I want even margins on either side, and be able to write your name 10 times. I'll just give you a minute. Give me an opportunity to have a drink. And if anyone is brave enough to share their results. So Wayne's done. Let's see how, that's nice. Nicely done. Okay. Very cool. Excellent. Wayne, I'll ask you, how uniform to your eye, because I'm looking at you as a tiny little picture right now, how uniform were you able to get those signatures?
Not bad. I mean, I'm pretty sloppy with my signature, so that there's some variation as I scroll through, but they're about the same height and the same width and in the same centering of the page.
So you can kind of see, like with that last signature, you can tell the fatigue is set in a little bit, right? Because the W is not the same, and then the Hetherington is kind of like, It's a really great signature, by the way. I like it. It's very stylish. Very,
Oh, thank you.
very, very nice. But you can sort of see in Wayne's signature how there are subtle changes, right? It's not completely, it's not like a stamp. There is subtle changes in the uniformity. Anybody else? Alexi, I see that. Yep, that's looking pretty good too. That's looking really uniform. But I expect no less from Alexi. He is a trained professional at these things. I do not do what he does at home. All right, so that's common cause variation. You can feel it pretty tangibly. You can do this demonstration with your teams to help them understand this. But let's take it up a notch. Let's repeat this exercise. This time, use your non-dominant hand. So if you're right-handed, you're going to use your left. With your left, you're going to use your right. See how you do.
So you're going to think I'm in kindergarten. This is horrible. I'm not even going to try to finish 10.
Mine somehow comes right to left.
Oh my!
Left to right.
Oh my God, Wayne, what happened?
Yeah, I reverted to my inner child.
So first of all, how did that feel doing that exercise, Wayne? Yeah.
Yeah, horrible.
Right? Like you're concentrating. It's not doing what you want it to do, right? Yeah. So the visual cortex, plus motor skill, the relationship isn't there. So I've introduced a devious special cause for variation in there. Overall, the systems are pretty much the same. Like visual cortex, processing, interpreting, decoding, getting some muscle skill, but the muscle has to be coordinated from a different place. So it's an extreme example, but we can have things like this happening in our organizations as well when there are changes outside of the domain of maybe the team room that introduce a different way that everyone is going to interact. And it's going to be kind of like trying to bring together the visual cortex and the motor skill, and it's dislocated, and you're seeing results like Wayne's signature. It's going to feel, you're going to see it like that kind of variation. When we're able to process that in a way, though, that is not, for what Wayne shows us is kind of like the summary statistic, right? It's not necessarily telling us why this occurred. We know why it occurred, but if we were just to look at Wayne's signature day by day and then this, we'd be like, what the hell happened, Wayne? Or did you come into work drunk? We're going to start to assign blame almost automatically to Wayne, even though we went and did something that changed how he could function. Thank you for being a good sport about that, Wayne.
Oh, no problem. It's just like Rob. I must have had a stroke. That in the castle of
Get some soda there. Okay, so now that we've had our quick lesson about extraordinary special causes versus common causes, we can get into some more nitty-gritty here. So this leads to leadership cheat code number 4. All systems vary in performance by some amount normally, and sometimes by some amount extraordinarily. Good system management depends on knowing how to tell one from the other. And you would be amazed at how many leaders and managers do not know how to tell one from the other. What you are learning here tonight is, I may as well be introducing you to the masons or the stonecutters. You're now in the guild of variation practitioners and students. You're going to know something that is going to change the way that you're able to look at the way your systems work. So along with 2 types of variation, we get 2 types of mistakes. So what we see in a lot of organizations is a misinterpretation of the phenomena that is occurring. So we've got variation occurring in 2 kinds of forms, common cause and special cause. Just like Wayne's signatures, we had all the neat signatures and then we had the special cause signatures. We can mistake one for the other because sometimes they travel in the guise of each other. So we could overreact to a common cause of variation, depending on how that variation is presented, or we could underreact or ignore a special cause of variation, thinking it's normal common cause. This happens all the time. Even with the knowledge of variation, you're going to make a mistake confusing one for the other. The best that we can hope for is minimize the opportunity. If we don't know, we are overwhelmingly going to make mistakes. I can give you one simple example for an overreaction to common causes of variation, where when I was working with a telco, they were looking for activation of devices, and teams were wanting to put together a dashboard. But the one thing that they provided to leadership with this dashboard is just a single figure. It said number of devices activated after this particular launch initiative had occurred. And it was showing the executive how many devices were activated per day. So you can imagine the number went up on some days, it went down on others, up, down, up, down, up, down. And of course, that created all kinds of anxiety in the executive every time it went down. He's like, why did it go down? So you end up marshaling forces to explain a change in a data point from one to the next. And that's not really an effective way to spend anybody's time. As it turned out, it took a lot of effort to even get this figure, because the systems that were available to produce that number had to be drawn from a lot of different subsystems. With underreacting to special causes of variation, this is literally the classic situation where you have warning signs, classic warning signs that a system is going to fail, and everyone just kind of, they've gotten used to it. It doesn't seem to mean anything until the big event happens. So, for example, we may get signals of security breaches in our systems, and when we go to investigate, we don't see anything. So on our, when we're looking at the data, we're saying, yeah, we had some things, but it never meant anything, so we ignored it. And then we have, of course, a legitimate special cause that occurs, and we missed it, and it happened way too late. We have a huge breach, and all of our data is on the internet. Being able to look at your data differently and be able to try and catch these mistakes that could inadvertently increase variation and make your job even harder to do is a skill. Again, this is something that not a lot of managers and leaders think about. Why do we overreact or underreact to the stimulus or the phenomena that occurs in our organization every day? So the challenge is this: if we're beset with common cause variation, and we want to know if there are signals of change, we've got to find a way to be able to highlight those within the data. So Dr. Donald Wheeler, who is a very proficient statistician, consulting statistician, expert in understanding variation and how to analyze for it in systems and processes. He says this: while every data set contains some noise, some contain signals. Therefore, before you can detect a signal, you must first filter out the noise. So what we're going to learn tonight is techniques that allow us to filter out noise and get signals from our system process data. So this begins, I just wanted to show this kind of as a historical artifact. This is the first not process behavior chart, it's called a statistical process control chart. And it was created by Dr. Walter Schuhart at Bell Labs in around 1924. So this particular one, this is a reproduction, an actual scan of his original mock-up. And what he shows here is a chart that is designed to report proportion defective in a series of manufactured parts. So one of the problems that Dr. Schuhart was assigned at Bell Labs was to understand what was creating waste in their telephone manufacturing processes. And they were narrowing it down to variation that was occurring in the parts that were being assembled. And some of those parts could be reworked, but some parts had to be scrapped. And he was tasked with understanding, well, why does it occur at all? So what he began to do was look at, well, let me just look at proportion defective. I'm going to plot it on a run chart, and I'm going to see what patterns it reveals. So let me just pull up a laser pointer here. So one of the things that you're able to see here is that he's got the data points in black here that represent the proportion defective, and they're all kind of around a mean. And I'm thinking this says 64. It's pretty grainy. It's hard to see, but 64% is the average. And he has what's called an upper control limit, and he has a lower control limit down here at the bottom. This represents what we call common cause variation from here to here. He's also included one for 1 sigma on either side, and there's a very important reason why he's done this, because this is a specific kind of control chart that's called a P chart. which deals with percentages. And when you're doing that, you're actually using a standard deviation formula. So when he has 1 sigma here, that is 1 standard deviation on either side of the mean. And then he calculated 3 above and below the mean here. So he says, we've got a point right here that's gone above the upper control limit in the observed points. And he says, okay, here in November, this point indicates trouble. That's what that word right underneath here is. That's why I've highlighted it. Very interesting. This is now over 100 years old. And he was beginning to figure out how could we take the data that is being generated every single day, every single week, and every single month inside of a factory in this case, and use it to be able to find when we had these causes occurring. So he could go to the foreman and he could say, what was happening here in November in the lots that were happening? Was there something in the materials we were receiving? Was there something in the machining? What was going on that we were having more percentages of defects being done there? I've got an article written about this, so you can see it in more detail. So there's the QR code for that if you want to snap a picture of that or just look it up on your phone. You can get more details about this particular chart. So the evolution, there's a number of evolutions that occurred over time from the P chart. In the 1940s, there was a fellow by the name of W.O. Janet who worked for the MO Valve Company, I believe, in the United Kingdom. And he developed a chart that was called the XMR chart. And that chart is, for all intents and purposes, identical to what I'm going to explain as a process behavior chart. You can use the two interchangeably. One of the interesting things about the history of the XMR chart is that it utilizes a process of analyzing the variation in the data that was originally derived from the ballistics field in the 1900s, late 1800s, early 1900s. That's called successive differences. So if you can imagine, you're firing projectiles repeatedly, and you're trying to know if you're landing on target. The successive differences between all of the shots and the distance to target. Wow, doesn't that sound familiar? Are we on target? Are we off target? That's what was being used all those years ago to be able to determine, were we sighting the guns correctly? Were they at the right angle, right charge, right muzzle velocity, etc. That informed Janet to create the XMR chart. So here it is canonically. This is how you visualize your process data in a way that you can interpret it for common and special cause variation. You can see there are two parts. The top chart is what we call the X or individuals chart. It has the data that we're wanting to analyze. Beneath that is the MR chart or the moving range chart. This contains information about the successive differences. So just as I was mentioning about how Janet converted the idea of ballistics calculations with successive differences, each point here, point to point, point to point, is reflected here as a delta. So the differences are all reflected here. What this chart allows us to see is this is the absolute difference, not positive or negative, just the absolute difference in variation. This gives us a very interesting picture about being able to understand how is the data varying point to point. This is used to calculate these things, the upper process limit and lower process limit. So just like Schuhard had, we've got a mean, which is the control line. And then above and below the mean, we have an upper process limit and a lower process limit. And for the moving range, we have the same thing. What we can see in this case is this is telling us for these data points, it's representative of a system that is under control. And this is actual data. I've got a friend who is a justice of the peace. And he came to me one day and he said, you'll love this. At the Ontario Courts of Justice, we have a guy who does stats. And every month we get together and we go over the stats about, how cases are being cleared or remands and stuff like that. He says we're clearing court cases at a rate of at trial of 4%. And I said, well, that's kind of interesting, but 4% of what? Over what period of time? And he said, well, I don't know. I said, well, that's pretty important because it could change depending on where you're sampling the data from. Was it the last quarter, the last year, last 6 months? They weren't really specific about that. So their stats guy was just keeping all over aggregate data for the year to date, and not really able, and sort of erasing with that summary statistic and just referring to the average, missing all of the variation that was occurring here. Now, one of the things that's kind of interesting about this is later on, this goes down. And they didn't have an actual way of interpreting or understanding that without being able to do this kind of analysis. So the idea of an XMR process behavior chart is it provides a quick economical test for us to understand whether our data are similar or not, whether we can see signals of special cause variation, because it would appear above or below these red lines. So what happens inside of the process limits themselves? We call these lines, these process limits, the voice of the process, because this captures the whole range of variation that this process could express. We could presuppose that if nothing else changes, we could continue these lines off into the future, and the process would behave exactly the same way, point to point to point. It would appear somewhere, between 3.4% and up to 5.5%. So we could reasonably predict where it would happen. But we would also have a way to say, well, if something changes, then we have an indication of when it changed. And now we can go and look very quickly, when did the voice of the process shift? Oh, one thing as well about the voice of the process, if I was to put a data point up here, and we were to press, for example, 6%, we want to clear 6% cases disposed after trial. The way that the system is currently configured right now, the Ontario Courts of Justice writ large Ontario, that's beyond the capability. As they are configured right now, they will never hit that. And that's actually been borne out by the data. So it can almost appear like a Svengali with this kind of knowledge, because you can understand when patterns in data shift. So these limits, they've got a particular way of being calculated. So you saw with the Schuhart chart, he used, because he was doing a P chart, he used standard deviations. When we're analyzing processes, we don't want to use standard deviations, and I'll explain why in a minute. The way that they are calculated is a different unit of measurement called a sigma unit of dispersion. So instead of 3 standard deviations above and below the mean, it's 3 sigma units of dispersion above and below the mean. It may seem like a lot of esoteric semantic gobbledygook, but there's actually a reason. And these units are calculated from, if I go back here, when we take the average of the moving range, that's used to provide the formula that tells us what to build these lines against. So the average of the moving range for the period, we go average plus 3 times the average of the moving range divided by some factor, which I'll explain. That gives us the upper limit. If we subtract it, the lower limit. These lines are not manufactured. They are not drawn arbitrarily. It is really important, a true XMR process behavior chart. These lines are representative of the variation in the data itself. So why 3 sigma units? This goes back a long way. The aggregating of data into subgroupings that coalesce around a mean has been known since the time of Laplace, and it's gone through various evolutions over time. With Dr. Schuhart, what he began to observe through many, many repeated experiments and observing how data worked from various sources, he built what's called the empirical rule, and several, others began to pick up on this and refine it over time. So it says that we can expect within a mean that 60 to 75% of the data will be within 1 sigma unit. That's a pretty good catchment, but it gets better. Usually within 2 sigma units, we'll find 90 to 98%. And by the time we get to 3, 99 to 100%. So the upshot of this is that we're creating a very conservative filter. If something is going to exceed the boundaries of the upper or lower process limit, you can be really, really sure that it is not going to give you a false positive or a false signal. The data has to be so extraordinarily dissimilar from its peers that it's got to break that 3 sigma unit boundary. And that's what makes this a fairly robust way of understanding whether we're seeing special or common cause in a data series. So here's another way to actually look at it. This is a process behavior chart that I created from a program that I put together in Python, some bit of code to simulate running red bead experiments. And this is 4 back-to-back red bead experiments. And the intent was to test a hypothesis to see where the data distribution would fall. And so, unsurprisingly to me, the mean settled down because when we're not using physical instruments, like the paddle and the bucket and the beads and the individuals all interacting together to pull a result, when you use just a random probability generator, any point or any simulated bead is the same as any other. There's no weighting. So I could pull white is just as much as I could pull red. So it didn't surprise me that given the configuration that there are 4,000 beads in an 80-20 mix, we've got 50 indentations. It didn't surprise me that 20% being red beads, that 20% of 50, 10, so that's the mean. And then we see the upper and lower process limits. It looks like it's about 1 here and probably 19 up here for this particular data set, and it fits the empirical rule perfectly. So in an ideal data series, an ideal data set, that's how we'll see it. And so this is also from my tool, PBC Analyzer Pro, which you can just flick a switch and you can see automatically how the distributions are how the data falls into the distributions. So you can see the 1 sigma, 2 sigma, 3 sigma. And so it just gives you a way to begin to appreciate and understand how this thing works and why it works the way it does. So you might be saying, well, you're talking about things that seem to be confusing with each other. Like we've got standard deviations, which are, an enumerative technique. Then we've got sigma units of dispersion. How are the two different? Again, you might be getting confused. And believe me, when I was first learning, I was confused. For a very long time, I made statistical process control charts using standard deviations and not understanding why I was doing it, because I was just following what Dr. Deming had done. Now, an interesting thing about the process behavior chart is that Deming didn't even know about it. Dr. Donald Wheeler, who refined it, who I mentioned earlier, he was responsible for sharing it with Deming in 1986 over dinner, famously. And it was because Wheeler had come across them decades earlier. He's like, how could you not know about this? But the knowledge had been lost, So Wheeler had been teaching it since 1971 at the University of Tennessee, and then he went on as a consulting engineer, a consulting statistician, and taught it to businesses throughout the 1970s and 1980s. He meets up with Deming, and he's like, oh, well, you should learn about this. So the difference between the two is a test, right? The standard deviation is what we call a global statistic. It presumes that all the data that we have inside of a frame that we're analyzing is the sum and the total. Remember I said the alpha and the omega. There is no data that's any different. Whereas a sigma unit of dispersion is a non-global estimate that simulates a standard deviation, but it's designed intentionally to see whether the presumption of similarity or sameness is true. And that's critical. One of the things you will find is that if you create process behavior charts using standard deviations, they mute signals. And I can demonstrate that. I'll actually show that when we get to the demo parts that are coming up. So let's see here, we're at 8 o'clock. So how do we interpret an PBC? How do we interpret a chart? Well, we've got an easy way to do that with 3 rules. So the first rule for finding special causes is pretty easy and pretty straightforward. Do we have any data points that are appearing above or below the upper or lower process limit on either chart? In this particular case, this is kind of interesting. Not a lot of people pay attention to the moving ranges chart, and I find that too bad. It is really valuable as a comparative analysis tool for this, because we can see that up here, the data is expressing these 3 points above, but then it drops below the mean here. This shows up as a significant point of variation, where it's going above the process limit down here. And this is again estimated at 3 sigma units of dispersion above the mean. And then we've got this particular data point here, which has hit the bottom. But look, the variation that is occurring from about here to here. So it looks like this V is really producing changes that are very subtle in variation here. That's kind of interesting. Just in and of itself, I would check some of that out. But there's another reason for that. We'll see that comes in rule number 2. So this is a more subtle signal that we want to look for inside of a process behavior chart. And this is when we get 8 or more consecutive data points that travel above or below the mean or control line. So as I was alluding to here in the previous one, this is kind of interesting. We've got this low period of variation and it's all traveling under the mean. Here, 8 points. This usually presages a change. So this means that the system or process is moving into a new state. So in this particular instance, the data that we're analyzing from the Ontario Courts of Justice, wait, this is not the right one, that's a different chart, wrong title. The data that we're seeing here suggests that the system is trending downwards. It's now going to start going around a new mean, right around here. So we could almost see that begin to occur. One thing we might want to do with this is recompute the limits from this point forward. That's a special technique called shifting the limits. My software makes that a breeze to do. It's a little tricky to do in Excel. I'll warn you straight up, not easy. Third special cause signal. I've adjusted this data. So this is a premium freight percent shipped by air. How many parcels are being shipped by premium freight? And they were really high at first and then they go down. So I shifted some of these points to be closer together. This is when you have 3 out of 4 consecutive data points closer to the lower process limit than they are to the mean. This is another indication. It's it's weaker than, it's definitely weaker than this, but when you combine it with rule 2, it's a strong signal that something is going to happen in the process, and we should be anticipating that the process could begin showing lower and lower performance. So we're operating in a way in this case where fewer and fewer packages are being shipped by air. So enough talk. Let's create one from scratch.
Sorry, Chris, before we move on to the next section, there were a couple of questions before. I think some of them were answered. So one of the questions was about the difference between a process control chart and a process behavioral chart. I think you covered that. I'm not sure if that sufficiently answered.
So statistical process control chart, that's the antecedent or the ancestor of the process behavior chart. It's still used in some instances in very specific data types. So when you're doing things that have binary conditions or follow the, here, let me get really nerdy for the stats people. If it follows the binomial theorem, where you have either or conditions, then you would probably want to use standard deviations. But the process behavior chart can work with any kind of data. Doesn't have to be normalized, can follow any distribution. It is robust enough that you can use it in a number of applications.
All right.
So we're aiming for 6 sigma accuracy. Very good, Nawaz. That's very funny.
Another clarification question was about the 2 control limits, that they are equidistant from the mean. And I think you mentioned that.
So it really depends on the, it can actually change, but it's still going to be equidistant because you're talking 3 units. So whether it's 3 sigma, meaning 3 standard deviations, or 3 sigma units of dispersion, that's going to be equal on either side of the mean, because literally the calculation is give me the mean plus 3 times the average of the moving range divided by a scaling factor. So it's plus, literally plus or minus. So it will be equidistant.
Will be equidistant. Okay.
Yep. But you can have like one of the, let me see, I can see some clarification that Rob has here. I believe they will be unless the lower limit bottoms out at 0. So you have to use some intelligence Sometimes your lower limit is going to be 0 because you can never have fewer than 0 things. But if you're analyzing data that can go negative, like say, for example, it's temperatures, then you would accept having a much lower, like you wouldn't truncate your process limit at 0. You would want to set it for whatever negative value it would be. So in that case, if you did set it to 0, yeah, it would seem like it's kind of not right, right? But if you're doing the full data series, then it should be, down into the negative. Again, something we can see. I can demonstrate this.
Okay. All right. I think that covers
Right.
all the questions, unless someone has another question before we proceed.
Okay, so here we are in our favorite application of all time, Excel. And one of the things that I've done here, I'm going to make this available. You can also find copies of this on my Substack, digestibledeming.substack.com. If you just search for template, you'll see that I mentioned it a number of times. But in this particular instance, I've got a lot of different goodies packed in here to make working with this easy. So one thing I'm just going to try to do here is just all right, go away toolbar. Okay, so I've got a basic process behavior chart that is set up here that is based on random figures. So one of the things you can see here is I've got rand between, and I'm goosing, a red bead experiment. You can use this to duplicate and create so that you can fill in your own values. But I'll use this to actually show you how the chart is put together inside of Excel. So we have the data point, we have the average. So I've highlighted this area to kind of make it easier to see. We're taking the average of the first 25 data points. Chris, you might be asking, why are you only doing that when you have so many data points? Well, limits, when you calculate them, begin to what we call harden as you get further and further out from about 25 to about 40 or 50. So you begin to lose their efficacy. You won't get anything. There's no economy of scale where more data points equals more sensitivity. What it begins to do is just shape the data in a particular way. So when you are analyzing your own data, try to restrict yourself to maybe 40 or so data points, 40 of the most recent if you can, so that you can begin to look for changes. So I've got the averages set up in a chain. So they're always equal to the one before. So it just cascades all the way down. And the reason that I do that is because it makes obviously updating them a little bit easier. So I could easily change this formula to go to 20 and it'll reflect automatically in the chart, right? Everything will be recalculated and fit that. So it makes it very, very quick to be able to go through the calculations. 25, 26, there we go. So I'm going to go back and change that. So next we have the moving range. That's what MR is. So average moving range. Moving range, you won't be surprised to find out it's the absolute difference between succeeding cells. So as you go down, each one is going to be a succeeding pair delta. So that gives us the moving range that appears down here. Next, we have the average of the moving range. This is always offset. So you can see it always fits the moving range. It's offset by one row because that's the difference, but it ends with the same row. So we're looking for the delta here, right here and here. And much in the same way that this average is computed, this average is computed. It's a series of chains. So we only have to change the topmost cell to reflect all of the changes in the data. So here's where the formula for calculating the limits comes up. And I'm going to be very careful and deliberate here, so I explain myself. And if you have questions, put a hand up, let Fernando know if I'm missing anything. So you can see very directly what's involved in the computation for the upper limit. We're taking the average and we're adding 3 times the average of the moving range. That's what we call MR bar. Like if you were to write this in notation, you'd write MR with a line on top. And then we divide it by 1.128. Why am I dividing it by a magic number? Because that's a well-established scaling factor that simulates the standard deviation for our purposes, right? Remember that this is only for the purpose of testing the homogeneity or similarness of the data. It's not actually, even though we're using math here, math is not the point. Finding signals is the point. If you have a signal that shows up near the line and you're like, it's not over the line, so it's not a signal. Guess what? Go check it out. The whole thing about this is to find signals in data, or to find something that looks like it could be a signal. Related to the question about will the limits be equidistant, you can see that in this particular chart, I've got two different lower process limit calculations. This particular one, all I'm doing is putting in 0 if it's a negative number. So that's what you see here, this calculation being. So for each row, these cells are going to change. It's just checking, is it less than 0? If it's less than 0, put a 0. If your purpose requires having a negative lower limit, you can absolutely do that. I've got this calculated here. So you can see for this particular data series, the mean is 23.64, but the lower process limit going negative is negative 4.5. There you go. There's a different calculation that we use to simulate the 3 sigma dispersion here. That's by multiplying MR bar by 3.268. Again, another scaling factor, well established. This used to come out of, in the old days in university, you would get books of tables of these scaling factors, depending on how you were doing particular analyses. So you would actually look up for particular applications, which scaling factor you would need. Any questions so far on what you're seeing here and how it's used? Nope. Okay. So let's go and look at, I've got some data over here in the source data tab. Does anybody remember Dan DeCanty's site, Actionable Agile? He used to have a, he used to have a free site, and you could play around with this dashboard of all these different metrics and that summary statistics. Well, a long time ago, I captured the data from his throughput chart. So we're going to use some of that. I'm going to grab, let's see, 40 rows. I'm just going to copy this. I'm going to go over here. I'm going to go to work items done. Let's get this tab open. Actually, I'm probably going to lose that data, so I've got to do something first. First thing I'm going to do is I'm going to get rid of all of these data points. Whoops. I'm just going to highlight those, delete. We're going to get a bunch of division by 0 errors. It's going to look like hell. That's okay, because we're going to go to the source data, and we're going to copy and paste straight into that. And if you want to know how I do this, all I was doing was duplicating the sample PBC, and I'm just putting new data in. This is the fastest way you can get a chart going, right? I've got this set up so that it looks at the first 25 data points. So these ones here, if I go, so when we're calculating our limits, we are using these data points. Of course, I went and wiped out my highlighting. Boom. So what do we see? On our chart, we see almost instantaneously that we've got signals, but I want to make sure that I'm grabbing all the data. So one thing I'm going to look at is make sure I got all my data points. Yep. You always double check. Sometimes when you're looking at this, when you're looking at the data, you might feel that you're missing some stuff. So always double check and make sure that all the data points are present, that your charts are accurate. Yep, looks like I've got everything. So applying our newfound skills of signal analysis inside of a process, we're using the first 25 data points, which takes us to the 13th of October. So if we just rest our pointer here, there we go, it goes up to there. So we're using that many data points. That's our baseline period. And we're testing how these data points work. So we can see that we've got some signals here. We've got definite rule 1 signal here. We've got 2 rule 1 signals here. So in this particular case, we've got 12 items, two high points where 12 items got shipped, another one where 10 got shipped. Everything else is below. So this is not a predictive process. So this is the reason I bring this particular data set up, is that the animated histogram that I showed you earlier, this is the data series it's based on. And that's why I said when I was looking at the data itself, I could see the variation in it because I've seen so many charts now. I know where the limits kind of would fall. So it's reconfirming my theory or my hypothesis that I was seeing uncontrolled variation. So what we would be most wanting to know is on these particular points, what was occurring? And I think for all of us having been in the business for a while, we might have some hypotheses about why these patterns occur. What do you think? What's your guess about why inside of this work item throughput, daily work item throughput chart on an SPC or a PBC, why are we seeing this? What could that be attributable to? What would be our theory?
Perhaps some process gates.
Process gates?
Process
So
gates.
things were,
Process gates.
yeah. So it was batching up and then getting released.
Some sort of batching, yeah.
Yep. That's possible. Other theories? I can tell you one that has occurred in my work. So I was working with a team in 2020, remote, Q1, and these points would correlate. I saw these kinds of points in their throughput, and they correlated to the product owner and some manager pitching in to get UAT done. And it was an unsustainable thing, but it would occur every 8 to 10 days, something like that would happen. And so you could see that pattern happening. There was a definite special cause of variation. So it stood out, and we were able to see that because we could put it onto the process behavior chart and monitor it right away. So this is in the folder, this PBC V1.3.3. You can use this to very quickly create your own process behavior charts. I've taken the drudgery out. I used to build these by hand for a while before I got smart and created a template. But even this is kind of this is good for if you don't know what else to do, right? You can pull up the template, you can put the data in, you can start analyzing process data, flow metric data almost instantaneously. However, you can imagine that there is a little bit of drudgery, especially if you have to start aligning your plot area with your data points. And what if you are wanting to analyze other parts of the data? So you're going to have to create multiple sheets sometimes to be able to look at the data and be able to interact with it. So that led to another epiphany. So I'm going to close this off so we can go look at some other data now that we've done this. So I'm just going to close that off. Okay, so if you're wanting to try this out, you can. PBC Analyzer Pro with dashes in there, onrender.com/free mode, capital M on the mode. And you can try this out for yourself. This is an alpha version. I've been working on this for 8 months. It began with a brain fart for being able to create process behavior charts without having to bring out Excel or automate Excel with macros. So I have a baked in Excel spreadsheet that is called up here. This is what it's based on. It actually pulls data out of a single Excel spreadsheet. The data is shown in columns of dates plus the data itself. And then you're able to select the column that you're interested in analyzing. So earlier we were talking about Ontario Courts of Justice. My friend who has this, let's see here, has his job as a justice of the peace, and this is the data that I've been keeping track of ever since he got the job. So some things to note about this application: once you load a particular chart, we have a switch for turning on percentages. So if our data is in percentages, we get that right away. And we have signals that are highlighted. So we've got the upper and lower process limits, very familiar here. Same here. We've got the mean, data points, but why are they in different colors? Okay, let me explain. In fact, I'm going to have to click some things here. I'm going to turn these off. These are rule 2. So right now I've got rule 1 signals presented right away. They're calculated for you automatically. You can see them up here. You can see them down here. You can say, okay, there's some interesting signals of special causes that are appearing here. But when I start putting on the rule 2, these are the 8 consecutive data points above and below the mean. We get the Christmas tree effect. It's starting to light up here. And this gets a little bit more interesting because you can have rule 1 and rule 2 signals in the same data series. So if I turn off the rule 1 signals here by clicking on them, now you can get a much clearer picture of where these 8 or more consecutive data points are appearing. It makes analysis really, really fast that you're able to do this. But the whole reason that I created this was I wanted to be able to determine if I could, can I test a hypothesis? So for example, if I decide that I want to only baseline using these data points here, I think it's about 30 odd data points, 31. So using this, I'm calculating process limits and extending them out into the future. And look at how the data begins to travel downwards. We're lit up with rule 1 and rule 2 signals. So it's giving us a very strong indication that this system has changed state. And that's one of the reasons why you want to use a process behavior chart, is it's able to give you very definitive ways to understand, is the prediction of the system working? Are the processes being operated predictably? When did it change? But wait, there's more. If we turn off baseline mode, we've got this hypothesis. We can do something called shifting the limits. And that's where we break the chart up into logical parts or contiguous parts, and we recalculate the limits each time. So say, for example, we wanted to recalculate chart here. I just clicked that data point. So right now, these series of data points are all revolving around a different mean. You can see it's 4.38, 5.47, 3.29. Then we've got all of these data points traveling here, showing different signals. This is kind of interesting because now we can begin to play around and say, well, how many more places can we break this up? Well, I might want to try doing one here at 60. Recalculate the limits. That's kind of interesting. So we've got this weird little kink that's happening, and you can see in the moving range chart how we've got this little valley that occurred. This is telling us that the variation was tightening. So we had wide variation here, the variation narrowed here, then it got wide again over here. Well, we might want to follow this variation out a little bit more. Like, what happens if I do this? And then I do this. All right, now I've got something interesting. No signals are presenting, but now I've got a chart that is very distinctly different from what we started with. What this is telling us is that, when you're able to follow the variation by breaking the chart up like this, by shifting the limits, and in this case, I've got it broken into 1, 2, 3, 4, 5 contiguous parts. This is not a stable system. Yes, Fernando. You have?
Yeah, what I was thinking is that I think that's where your understanding of the context becomes really important, right? So systems don't occur in the vacuum, they occur in some context. So
Exactly.
So you need to see, well, because you can just visually look at the chart and say, well, what if I move the range here? Or what if I consider the average to be lower here or higher there? But I think that's worth thinking about. Well, what happened around that date? So
exactly.
You're saying, well, these are court cases. So you could say, well, this is the date when we decided to implement, the new case system, and maybe that shifted the average. Or this is the case. This is the day where the pandemic started, and that's just
yeah.
Or,
yeah. So one of the things that's interesting about hello, come back. That's lower chart. One of the interesting things about this is there's a particular date here that has special significance, and it's this one right here. And this is the date that a Supreme Court decision was handed down about the right to an expedient trial. And the idea was that if you are going through the system, the court system, you have the right to be heard and tried within 18 months. So the theory was, the Supreme Court has now given you a rule, 18 months or the case gets dismissed. So you would expect to see this figure traveling a little bit higher, but the immediate impact was to depress. Now it's slowly coming back up. but it's not necessarily where you would expect it. So when you play with the shifting the limits, you've got to do it with, as you say, a little bit of context. And there's also what kind of story are you trying to tell with the data? So you've got to back it up with some figures. You got to be able to say what occurred at these points that are interesting. And then how do we translate that into something that we can share so that we can pull out an analysis? So I'm just going to reset that chart. So let me take a look. Tell me if can you see this?
Yes.
Okay, all right. So this, I'm running this locally. I also have this, but it's only available to paid tier subscribers for my newsletter. So I'm running it locally on my system here for the moment. But I wanted to be able to upload the data that Mike sent me. So let me go to, sorry, Fernando. We'll try to get to your data, but let's see if we can bring up Mike's data. Mike Bowler data, clean. All right. One of the things to note about this application is it gives you a quote to kind of set your mind in the right frame for the kind of work that you're doing. So you see the quote here that comes from Donald Wheeler about noise and signals. I've got about 22 of them that come up randomly. And that's principally because this is aimed at being a teaching aid. So let's have a look. So Mike sent me some data and I was able to play around with it. This is flow metric data. So one of the first things that he sent me was blocked whip. I thought this was interesting. So you'll notice that it comes up looking like modern art. And that is because it doesn't automatically detect the date properly. I'm working on it. So I've got to change my date format so it's daily. All right, so now we can actually see. So we've got some analysis here. This is daily data, so you can actually see there are dates that are attached to each one. They're sanitized dates, though. These aren't the real dates. We can see here we've got 151 data points, so a nice spread, but it's lit up like a Christmas tree. We've got all kinds of variation that is occurring, and it suggests that we have multiple things going on. So if I was to do an analysis on this, I would pop into baseline mode, and I'd say, well, let's see what happens if I try to pull this variation out here. Well, these points are still, 0 is 0, so we've got some interesting stuff happening there. I see that there is some exceptional variation over here. So what if I was to baseline on this? Very interesting. So I get kind of, just by playing with baselining this chart, I still get some signals, but it's very noisy data, right? This is a system where if you were aggregating this data and basing predictions on it, I'd be hedging a little bit because it's fluctuating so much. We have a period here which seems to have some uniformity, but not really. Then it goes through a kind of a wild period here where it picks up a little bit, but then it drops back down again. So there's a lot going on inside of this particular data set. But I found it really interesting. It's a great way to understand, okay, this is what it could look like. Then we looked at total width. Now this, I believe, oh yeah, this is still modern art. Okay, let's do that. All right, so here's something that's kind of interesting. Definite mountain ranges. So when you see your data looking like this, you may have too much. You may want to break it down. But you can definitely see that if we were to baseline, oh, that's not baselining. Reset chart. If we were to baseline over here-ish, let's say here. Almost. Again, really noisy data. But what this is telling me over here, there's definitely a new change. There's a change that occurred in the system that was bringing total whip up, daily whip up, like this, into a whole new period, a whole new state. So this is a definite indication of, like, when I see this happening, I'm like, oh, okay, let's go try playing with shifting the limits, and let's see what occurs. Like, is it possible to capture this variation in any way? And I'm like, not really. It starts to get kind of crazy. So this
Actually,
is. Yep, sorry.
If you reset it back to the origin.
Yeah, this is reset back to normal. Yep.
Okay, so because I think the conclusion I would draw at that point is that somehow the system is trending up, right? So you start down, below, down,
Yeah, here.
low side on the left side, and then it starts going up and up and up, and somehow it comes down. So how I'm thinking, so what kind of analysis would you do there? Because just shifting the average, I don't think will help, because it's obviously kind of going always up, right? It's kind of like
Yeah, well,
on a trajectory up, and somehow it settles down again.
yeah. So it's all of this is telling me no matter how I play with this, I'm getting signals, right?
Right.
As I'm trying to capture the variation. It's going up, it's going down. This is an unstable system.
Yeah, but there's
So
definitely something happening there where you have the arrow, because that's the change in the trend, right? So the trend seems to be changing, going in the opposite direction in that date.
yeah, I'd be wanting to know what's happening down here.
Mm.
This is where I'd be wanting to complement this analysis with this
Mm-hmm.
and say, what is the variation point to point telling me? We don't really use trend lines inside of a process behavior chart. We're not concerned with trend as much because trends are tent poles, right? They kind of stand on points of data and they say, oh, by and large, on average, how is it going? Can we fit it to a curve or a line? That's a different analysis. I would complement. I would say, okay, do a trend analysis. But the purpose of putting this into a process behavior chart is to understand, is this process operating predictably? My conclusion on just looking at this is no, this is a chaotic process. Now, there could be very good reasons for that. I don't know. I have to know more. I can say, though, that I've had similar patterns to this occur in teams I've worked with, and it's an indication of tampering. So something is causing the changes. So use your head when you're doing this kind of analysis. Don't just rely on the lines. Just look at it and say, wow, there's a lot going on here. Let's go have a conversation with the people doing the work. What's happening?
And comparing this with some other chart. So I would be
Yeah.
curious to see
Yeah.
what happens in your CFD here, right? What
Oh,
kind of
yeah.
CFD telling you here, right?
Yeah.
So,
Yeah.
Brad
Absolutely.
has a comment.
Yes. Go ahead, caller.
Brad?
Oh, no.
Yeah. It's
Yeah, it was just observation, right? This is based on total whip, correct? Right.
daily. Yeah. Daily total whip.
Yeah, so I mean, if it's fluctuating, that's telling me they're not controlling it. If they're not controlling it, it's unstable, right? So
Perfect.
yeah.
Yeah.
So,
Perfect. And
so
this is something. Oh, sorry, Brad. Go ahead.
oh yeah, I'm just speculating, right? Why is it going up and down, right? Well, hey, maybe there's some management injection, injection, or yeah, or they're not valuing the flow and the value of limiting whip, right?
That's correct. Yep.
Yeah.
So it gives you like this whole thing gives you something that you can go to leadership with. You can actually you can export these things and say, what did we do here? What did we do here? If we can tie that to something that changed in the organization or changed in the team space, perhaps we were churning through people. Now we can point to cause and effect, right? This begins to change the tenor of management because now no longer is it just blind reaction or guessing or intuition or gut feel. You're now able to approach it systematically. You can say, look, you had a theory that this particular change would produce lower total whip per day. It's done the opposite. What do we think about that?
Yeah. Have you done an experiment? Just correlate this, do a similar one looking at the throughput.
Brad,
Like,
Chris, I just want to throw out some idea. Like, actually, Fernando and I have seen this sort of whip behavior kind of going up and down and with pretty significant swings. And what was happening there was basically there was a weak whip control that worked like this. When there was a trend going up, there would be a countering force to bring it down from the management. However, that force was pretty weak, so the actual whip would keep going up. But the higher it goes, the stronger the countering force gets. And at some point, there is an absolute ceiling where it is going to push it down. And the same force from the bottom, although understandably, it would actually start countering a bit sooner. So if whip is going down, there is a force that actually wants to push more work into the system. Understandable. But it's
ironically,
relatively weak. Unless WIP drops to near zero, then of course it becomes quite strong because it cannot tolerate it. So in effect, like what we actually saw once, but I mean the main overarching point here is that you do have to like study what's actually happening inside the process.
Yes.
And all sorts of interconnected forces affecting it. But basically the weak countering force, which basically like keeps it within a very wide range, right? But it's still going to swing back and forth quite a bit. Kind of that was the outline of the total system in that particular case. I'm not saying something like this should necessarily be here. I'm just throwing out as an example of a variety of things that a variety of weird things that can be happening inside processes.
Right. And that's why you've got to be very, very careful about using these. You can't just armchair quarterback. They give you a place to begin thinking, but you've got to complement that with going out and doing the work, right? This isn't a substitute for just sitting back and saying, here's where your problem is. This is a way of being able to look at what is the system saying. Am I interpreting it correctly? And the thing to also remember is even a overt signal can be a misinterpreted signal. So even though we've got some things that are appearing in red here, they could be very well explained, right? While I've got everybody here, I just thought I'd show what does it look like if we use standard deviations to calculate the limits here. So if you click that line, so now I'm using 3 standard deviations from the mean, you can notice that the signals, all but these ones, disappear, right? And this is what's meant by standard deviation being a global statistic. And when I'm using the moving range to calculate the limits, it's different, very different. This is useless. This is a little bit more useful. But the thing that's offsetting this as well is we're calculating it across 151 data points. To be really useful, we want to make sure that we're looking at a portion of the system that we're concerned about. So say, for example, is this representative of the new system? If I baseline here and I say, let me calculate limits like this tells me very distinctly there was a way the system operated before, and it looks like there's a way the system is going to operate after. So even though we've got signals here, this is kind of interesting. Another way to do the analysis. Cycle time. This one, Mike had this arranged in such a way that we had multiple data points that were occurring on the same day. So that's why I don't have dates attached to this. I've just got them numerically, but this is the order. I tried to preserve the order of the data, and that's really important. When you're analyzing the data in the PBC, preserve the time order as much as possible. Otherwise, it's useless. But again, we get some really interesting signals here, just based on this data. If we were to baseline, pretty extreme here, maybe 30 or so data points here, 34 data points. We baseline at that, we can kind of see periods of predictability. Some interesting areas where it looks like some change could have happened, but then it spikes up again, definite signals occurring. Were we to baseline here, doesn't really change the picture that much, right? There's some interesting places, like the extreme ones, you don't really need permission to go and figure out, I've got a list now of places to go look. Tell me what happened here. Why is the cycle time, why was it up at 27 here? What did that represent? What got stuck in the system for 27 days? But you can see as well, how effective is a mean at communicating? So if your mean is 4.1, look at all the variation that's gathered around it. Your upper process limit is 12 based on this range of data. It's a long, that's a range from 0 to 12. So cautionary tale for relying on averages. So I wanted to know about daily arrival rates. So we looked at this, modern art. Yeah. That's looking pretty stable. pretty regular. Upper process limit of 4, mean of 1.8, clicking along like tickety-boo. Nothing wrong here. And it looks pretty healthy.
Sorry, Hino has a question about that baseline window.
Yep.
He asks,
Okay. Yep.
when you're creating that baseline, does it leave out the outliers, the ones above and below the selected area?
No, it calculates them. It's just the way that it's drawn. I just draw the box inside of the limits. So if I was, oh, wait a minute. That's zooming in. Stop zooming. If I do something like this, am I excluding other data points? And it's like, no. I'm just drawing the box between the limits.
You're essentially just taking the data points in the window to calculate the others, not leaving. So it would include any data point that is outlier, that is, extreme.
It includes these. So anywhere between, anywhere that the data points appear, that's why I have the highlight box. It tells you 13 data points. So these data points are calculating the mean and the process limits for the rest of the data. And that's where this tool has some power and flexibility, because if you do it in Excel, typically you're always going to be coming from here, right? You're going to be doing the first, 24, 25 data points, not the whole data set, because you're wanting to see, are the limits predicting the future performance of the system? But what if you want to know, I want to shift this. I want to say, well, maybe the system here is more interesting. This is more representative. There are changes that occur. Okay, well, if that's more representative, look at what it does. Now we're getting signals because I'm calculating the limits forward and backwards from this data here.
I had actually a question about the if we can go back to the cycle time chart you were showing.
Okay, just give me a second.
Because what I was thinking is that we know that cycle time distributions tend to have this more extreme and asymmetric shape, right?
Okay, let me just pick the data column. So which one, the cycle time days?
Yeah, go back to the cycle time, because I think that, so you have that data point kind of in the center is very extreme, the one you pointed that one, 20.
Yep.
So
Yep.
yes, it is very extreme, but it may be just related to some delay that is actually baked into our process. It's just very unfrequent, right? That's the case when we happen to touch this particular module of the system that requires special authorization from legal, right? And so there's nothing unusual of that. It's just simply that we don't do that very often, right?
Yep. So that is a fantastic case in point where you can go just have a conversation. What happens in traditional management circles is it goes to 27 and somebody loses their mind, right? And it automatically becomes something to apply pressure to, explain why it went to 27. Whereas you have a different conversation when you say, oh, isn't that interesting? All the other data points are below the limit except for this and 2 others. Isn't that interesting? And you could find a simple conversation, like you said, it could be something that goes through regulatory or legal that has a longer cycle time. There you go, problem solved. It doesn't mean that something bad has happened. It just means something is interesting has happened, and we want to go find out why. And this makes it very clear, yeah. And you might say, looking at this, why do we need the process limits? Because you could just say, well, it's right there, dummy. But it's when it gets a little more subtle, when you have different things that are occurring and you want to know, like even this point here that isn't necessarily over the limit, I'd still want to have some conversations around what's happening here. It's getting really, really close. What would I like to see that be? What is the ideal? So for cycle time, I'd like to see this come down. How do I get the variation in the cycle time to be managed downwards? I'm not going to get rid of it all, but what would it take to bring that mean down? So we have different.
Just to comment on your and Fernando's exchange, typically when we see this sort of pattern in time matrix, often comes down not just to a single cause, whether a cause of delay, but like several of them present in the process, and then the unlucky work item, and they're probabilistic, and the unlucky work item hit like all of them. So it's like basically
Good
when
point.
you are out, let's say driving on a boulevard, and you hit traffic lights. As you know, I told this story many times because I was in the habit of driving on a boulevard that had 13 traffic lights between you know, the highway exit and the place where I was going. So like it's an unlucky work item that happened to hit maybe 9 or 10 red lights, whereas the typical cases you hit only 2 or 3.
Yep.
And basically it happens for no particular reason. And that combination is relatively rare. It could be like 1%, like if you like run the numbers. So you may not see it in a while. And actually 1% probability doesn't translate it into, if you have a sample size 100, you're going to see one of them. You actually have pretty good chance of seeing none of them in that window, and sometimes seeing 2 or 3 in the same window. And that's why these like annoying outliers are quite like that's why they're annoying. But they often have some reasons baked into the system.
Oh yeah.
As Fernando
Yes.
said. So,
yeah.
But I mean, once again, it comes down to actually like knowing what's inside the process and studying it from the inside.
Precisely. This
Using
is not
perhaps this as a signal or motivation. Actually, like this type of I don't really like the word outlier, but okay, well, people are gonna call it that. Is actually almost always a treasure trove of what delays occur in the process, because I mean this item hit almost all of them, right?
Yeah.
Whereas other items only hit some of them, and that's why they show faster performance. But we can retrospect on that item, actually uncover a lot of interesting things we didn't know before.
Yeah. Oh yeah. Yeah. And imagine having retrospectives, point retrospectives, where you're looking at this data every other day. You know, that it changes the conversation that you're going to have, the quality of the conversation. And you're going to be able to share this information with more people, because it's so easy to interpret. Once you begin to just understand the underlying theory and can explain how it works and why it works and what you use it for, now you've got something interesting to share and have interesting conversations. We got 2 more messages. Oop, not just averages, the whole distributions. Yeah, you are the only other person I've met that is counted for. You've got a nice, Wayne. That's awesome.
How did you know?
All right.
I used to do that because it just, driving is boring. And so I started counting traffic lights, and it's like, why am I getting so many reds all the time? So Alexa, I'm with you on that one.
See, you could capture that data, put it into a PBC, and then you're going to understand what's normal and what isn't normal. I tell you, once you start using this technique, it's hard to not look at data. You want to do it. You want to, is this stable? Is it within control limits? All right, so let me just get back to the deck, and then we can close off here. All right, so we've created one. We've done some flow metrics. We looked at the free mode demo. So just remember that URL, PBC Analyzer Pro on render.com/free mode. You can go and play around with the different charts that I've put in there. Sometimes I change the data set. So from time to time, you may see there's new data series, but it'll give you an idea of how to play around with it. Okay, so recap. Variation, universal phenomenon, comes in 2 flavors, common and special cause. If you're in the game of predicting processes and how they work, it depends on knowing how to tell one from the other. And the process behavior chart makes that really easy to do. Makes it quite dead simple. So you want to use them wherever you need to be able to sort out or complement what you're seeing inside of a summary statistic. So I'd encourage using it. Pair it with the analyses that you're doing right now, so you can see whether the processes that are creating those patterns are stable and predictable. And remember, empirical evidence is never complete. That's why you do it. This is for Alexi. I found this. Dr. Wheeler has tested this over many decades, the process behavior chart method with many different distributions of data. So can you do it? Is there, has someone actually tested and tried it? Yes, across many different sources. So that's why Wheeler calls it the Swiss Army knife of analysis tools. So don't be afraid to add it to your complement to your roster. I've written some articles on my Substack that you can learn more about. This will be in the deck that I'll put into the downloads folder, so don't worry about it if you don't snap everything right now. But I've written a lot about this, a lot about Deming's theory, about Schuhart, Wheeler. I write about this stuff all the time. Books that you might want to pick up that are related to what you've heard tonight, especially the two in the middle. Those two books by Wheeler changed me incredibly. They explain how this works right down to the nuts and bolts really, really well. Wheeler is a fantastic explainer. The 20 things you need to know if you really want to know how process behavior charts work on the inside, the math, when to apply different things, how do the process limits really work, what are the degrees of freedom, all of these things. They're a great, those two books together, amazing. If you're wanting to teach leadership about this, Mark Graben's book, Measures of Success, highly recommend. Because Mark is able to describe it in a very non-threatening way, and he was taught by Wheeler. So there's a direct relationship in the knowledge sharing. And of course, as always, the New Economics, that's where this all began for me. You can find my newsletter here. It's digestibledeming.substack.com, but you can get it through that QR code. Thank you very much. That's it. That's all.
All right. Well, thank you, Chris, for the presentation. Let's give him a round of applause. And
thank you.
Would anyone have any additional questions or comments before we close the session for the night?
I guess I have one. I'm kind of hesitant to bring it up, but I've kind of had a visceral reaction in the past whenever I've seen a what's called a control chart, either in Jira or something else. Right.
Yeah.
Right. And especially when, hey, we're talking about people, we're not talking about machines, right?
Yep.
So, so let's get rid of the upper control limit, lower control limit. Let's just look at the outliers and, and maybe the trend as well, if they do have it, a rolling average type of thing. So, so yeah, I do see the efficacy of this specifically, and yeah, I want to drill down, and provide more analysis. But it does take a little bit of, extra, knowledge or explaining, hey, here's how it works, right? So it doesn't come across, hey, here, team, you're out of control. So
yeah.
So anyway, any kind of insights just on all of that. Or reflection.
So Mike had in his session, I didn't include the slide of it, but it showed what the Jira control chart looks like, and it is not a control chart. It's like, even for practitioners who would use it in manufacturing purposes, that's an abomination. I don't even know what it is. Wheeler changed the nomenclature for the chart deliberately because of the points you've raised. Because, he said control limits kind of suggest something that, it's not just the process you're wanting to control, but the people. And so that's why he changed the name to a process behavior chart and said these are the process limits, because he was wanting to reinforce continually it's about the process, right? The majority of performance belongs to the process. That's what the red bead experiment shows us. We can put different people in the same system and they're going to get the same results. It doesn't matter. The thing that we need to repair or improve is the system. So what I find is when I'm able to show leadership these kinds of charts, I bring them into it really gradual and slow. I don't even make a big deal about it. I just say, I was looking at some stuff and I saw something interesting. I'd like to share it. Here's something you might find interesting. Would you like to learn more about it? And I almost find that the charts themselves, because a lot of folks in teams, but especially managers, they love data and charts, but they don't know how to use them, right? So we get those situations where distributions and means and different toys that we can use in stats in Jira get abused and turned into policies. And we don't necessarily want that, right? We want smart, intelligent conversations about improvement of quality. So there's way more. So you picked up on it very well, is that this is just the opening. This is kind of like the gateway drug. In understanding why and what this is communicating to you, I've only scratched the surface, and I blew my time in any event. So,
Thank
so
you for
that
that.
your points are valid completely.
Just slightly over 45 minutes, Chris. Just a bit.
Yeah.
Just a little bit.
Yeah. But
was,
I knew that I had a 2-hour time box.
there was an earlier comment also from Hino, because you at some point you were pointing out that you would show these diagrams very frequently, and his observation was, wouldn't every other day be too often? Would it not drive knee-jerk reactions?
It could, but it's on the mindset, right? So if this kind of material is being updated all the time, it's up to the individual team or group. That you could say, well, by observing the process too frequently, am I creating an opportunity for a special cause to occur? Maybe, but I can tell you when I work with teams, one of the things I do is I update the charts every day. If I have to pull data, I'm always seeing and updating the data. The team might not see it every day because they're busy. So I might wait to share it with them, on a Friday when we're just chilling. But sometimes I've had leadership actually ask me, they're curious. They're like, how does it evolve? How's it going? And being able to provide, charts that are fresh, up to date, and I can explain, and especially if I can re-baseline them too. That's where the tool becomes really, really effective, is because I can actually change the baseline. I can say we're in a new period now. So the old data doesn't matter. We don't need to know what happened 3 months ago. The current month is providing us great data about how the team is working. So now let's use that. But yeah, use your judgment.
Yeah, but that's where, sorry, it's the first time I talk, I know. So that's where the you're actually mitigating that that risk already, right? By actually giving them the data only on a Friday, and by allowing the data somewhat to settle and see that there's variation, so that there's no immediate knee-jerk reactions, right?
Yeah.
Okay. So it depends on how knowledgeable you are about the data and about how to interpret them, whether or not this makes sense to see them every day.
Yeah. And that's why you would want to kind of bring everybody along. Don't just spring it on them and say, here's a new way to measure you. Like teach the method. Say, I've learned something new. I'd like to share it with you. I think you're going to find it interesting. Let's try it out. And then, when would you like to see this? When would you like to know more about this? Right. So pick your frequency accordingly. But good point,
All right.
So is that it? We're good.
Any final questions? If not, then thank you so much, everyone. Thank you, Chris, for the presentation and the discussion. And thank you, everybody else, for participating. And stay tuned for future announcements. We'll see you at future Kanban sessions.